Hi guys, my name is Gary Stewart with the Summer REU program here at Alabama A&M. I'm from Colorado Mesa University, and as we told last time, I'm doing glycerol as a carrier for the Gold-3 ion, and it's an anti-cancer, antimicrobial application. Last time I talked about some background info about 1965. They discovered that metal ions would do this job of killing cancer cells, and we wanted to see if glycerol derivatives could be used to get our diethylphosphoric acid that's used to transport these ions. Has applications, as I said, in cancer and antimicrobial applications, where not only will it kill cancer cells, it can also be used to kill some like streptococcus bacteria and stuff like that. Food poisoning applications and stuff. It's a feasible economic source, the glycerol, for mass production of the medications if we can get the synthesis to happen. Before going to setup and prep work, basically just to show the chemical formulas, I'm going to go ahead and write these down because I'll use these later. And I'm just going to do these on the whiteboard because it's just simply for ease of operation. For glycerol, the chemical formula is C3H8O3. We're going to react that with trimethylsilane, chlorotrimethylsilane, which has a chemical formula of CH3. 3 of these contained in the chain, and a silicon chloride combo there. These will react, and out of these, we're going to get, for 1-to-1 ratios, we're going to get For the 1-to-1 ratios, we're going to evolve our compound. It's going to have 6 carbon atoms, 16 hydrogen atoms, and we're going to bond up. And what happens is our silicon and this CH3, this methyl atom, are going to bond together. And what that's going to do is give us what we call a protected ligand. These protected ligands protect this vehicle, this chain, from side reactions as it travels through the body. Now, in the 1-to-1 ratio, we only get to protect one ligand. It looks something like I'm running out of space here, but your silicon links up with your methyl. They bond back to the oxygen, and actually the carbon wants to bond to the oxygen, but as we write it out in stoichiometry, this is what it looks like. So that's what our protected ligands look like. For the 1-to-1 ratios, we're only going to get that one protected ligand. 1-to-2, we're going to protect 2 ligands. So essentially that's how that all falls out in the stoichiometry part of it. Now, what I had to do, after I figured out all this, I calculated my my quantities that I would need for stuff, just to get ahead of the game. But the first thing I wanted to do was get all the stuff cleaned, because before I did anything, I couldn't have any external contaminants affecting my reaction, because I have a lot of volatile stuff that I'm dealing with. And the idea with this is humidity is a big factor. Water vapor can't be introduced because of its reaction with the phosphorus pentosulfide later on. So we have to really be careful about letting this stuff hydrolyze, meaning uptake of water molecules and stuff like that. So the setup and prep work was a big part of getting started. I spent actually a whole day doing that. Break down existing setups within there. When I walked in that lab, it was a happy mess. I had to clean the hoods with acetone because it had stuff all over it. So I took acetone, cleaned all the hoods off. Followed that with a soapy solution to neutralize the acetone. Then I just did some general house cleaning, got familiar with all my stuff in the lab, figured out where all my glassware and stuff like that was. I washed my glassware next, and I did that. What we did, we want to get all the acids and alkaline solutions off of my glassware that somebody else might have left. So to do that, I do a 2-stage process. I produce a sodium hydroxide bath with water. I just take some sodium hydroxide pellets, drop them in water, let them dissolve. It gives me a good alkali bath, which is it makes us an organic salt. Then we took sulfuric acid and potassium chromate and made a chromic acid. I synthesized some chromic acid, made a bath with that, and then reacted glassware with that to get any other stuff out of there. It completely breaks down any soils, dirts, human contaminants, or anything like that. After each bath, we washed it real thoroughly with water, just regular tap water. No need for distilled water at this point. Then I took ethyl alcohol, wiped each of them down, swished it around and all that. And what the ethyl alcohol does is serve to help evaporate the water out. And we've got dryers up there in the chemistry lab that each of these pieces of glassware were dried for 24 hours between each bath prior to being placed in the other ones. Once again, humidity control. Next, I was collecting all my chemicals, getting everything ready because I like to work efficiently. So I spent time getting everything ready. I had to get my benzene, glycerol, chloral trimethylsilane, triethylamine, and I gathered my safety gate on because I want to know, what am I working with? Is this explosive and stuff like that? And MSDS sheets are what I got, material safety data sheets. Basically, anytime you're working with chemicals or stuff like this, you want to have these around because here in the university environment, you're not really going to see it, but in a commercial environment, you have OSHA that could pop in on your stuff like that, and they're going to want to see these MSDS sheets, especially if you have other people working on this. It's required by law that you have these around when you're doing this. My initial considerations were just wanted to see what happens in the reaction of glycerol and chloral trimethylsilane. I just wanted to see, what's going to happen. When I mix these two together, what are we going to get? So I composed samples initially in a test tube via a Dwight-wise addition. And everything we do, anytime I'm adding chemicals, I go to the dryer and open the door, and I do it in the atmosphere of the dryer, in the local atmosphere that the dryer gives me. The reason, once again, humidity control. In other universities, they use nitrogen, liquid nitrogen, gaseous liquid nitrogen, to kind of evaporate the water out of the air. But we don't have nitrogen lines in the lab, so this is our alternative method. I reacted 2 samples, the 1-to-1 and 1-to-2 molar ratios that I'd shown you earlier. These yield that hydrogen chloride gas as a byproduct. As soon as hydrogen chloride gas reaches water, it becomes hydrochloric acid. So a quick sniff test, you can sense some hydrogen chloride gas. It's going to burn. It's got a very foul odor, and it's really exemplary of hydrogen chloride gas. So, and if you notice, you get 1 mole of hydrogen chloride gas for every 1-to-1 ratio reaction in 2 molar. So whenever you react this one, you want to do these under a hood. You want to make sure that you've got that sealed till you get under a hood because it's going to generate that gas quite fast. It's not a very vigorous reaction. However, the gas liberates and gets out pretty quick. In the initial stuff, we just added triethylamine as a catalyst. It serves to neutralize the hydrogen chloride gas. What you get out of it is an ammonium chloride gas, and it neutralizes the acidic properties. Later on, we, as you see in our batches, I didn't mix this as a catalyst. We determined that the reactions would actually occur without adding the catalyst. But what we decided to do with the triethylamine is use it as a tester to see if we were generating hydrogen chloride gas in our reactions. And this was our first indicator that the reactions had taken place. The initial results I got out of that, once I reacted everything, we noticed as soon as you put the chloral trimethylsilane into the glycerol, it forms a colorless, viscous fluid at the bottom. It gets a little bit denser than the benzene. I use the benzene as a reaction medium. Benzene's not reacting with either the glycerol or the silane solution. So it's a good medium to do your reactions because most of your chemical reactions, you want to give them a good non-reactive medium to be stirred in and get the good reactions. Once again, I said I tested for the evolution of the HCl gas with triethylamine. It forms a white cloud. As soon as you stick it over the vapor cloud that's being generated by the reactions, you'll see a formed white cloud. If you take and react that, as I did in some of the first stuff, just testing, excess triethylamine will cause this to evaporate entirely into a white precipitate. It becomes an anhydrous precipitate in the base of anything it's at and can be redissolved once again. My test passed, so I knew my reactions had occurred. Next, I need to get me some samples for analysis. Need